A jet engine swallows enough air every second to fill a two-bedroom apartment. It compresses that air until it's several times hotter than your oven at maximum heat. And it does this thousands of times every single flight without melting itself apart. Most people think a jet engine just sucks air in and blasts it out the back. That explanation isn't wrong, it's just incomplete. It's like saying a computer works because electricity goes in and pictures come out. Today, we're going to open up a jet engine stage by stage and understand what's actually happening inside, the physics, the engineering compromises, and the reason this machine is considered one of the greatest achievements in mechanical engineering history. By the end of this video, you'll understand why the engine's own exhaust is what keeps it from destroying itself. Every jet engine, no matter how advanced, obeys one simple rule: Newton's third law. For every action, there's an equal and opposite reaction. A jet engine's entire job is to take in a mass of air and throw it backward as fast and as forcefully as possible. The reaction to that backward push is a forward force on the engine. And since the engine is bolted to the aircraft gets pushed forward too. That's it. That's the whole principle. The complexity isn't in the concept. It's in how you accelerate that air efficiently, safely, and repeatedly. Tens of thousands of times at 35,000 feet in freezing temperatures without the engine tearing itself apart. To do that, engineers break the process into 4 stages: intake, compression, combustion, and exhaust. Let's go through each one. Air enters through the front of the engine, through what's called the intake or inlet. This sounds trivial, but it's a serious piece of engineering on its own. The air arriving at the front of a jet engine is moving fast, sometimes close to the speed of sound relative to the aircraft. But the compressor blades behind it can only work efficiently on air moving at a much slower, controlled speed. So the inlet's job is to slow that air down and smooth it out without creating turbulence before it ever reaches the moving parts. On commercial engines, you'll also notice a giant fan right at the front. This is the first thing you see when you look into an engine. This fan does 2 jobs. A portion of the air it pulls in goes into the engine core to be compressed and burned. But a much larger portion, on modern engines often 5 to 8 times more air, is pushed around the outside of the core entirely. This is called bypass air, and it's one of the most important ideas in modern jet propulsion. We'll come back to why in a few minutes. The air that does enter the core now passes through the compressor, a long series of spinning blade discs alternating with stationary blades called stators. Here's the key idea. Each stage of the compressor squeezes the air into a smaller space. Smaller space, same amount of air, means the pressure and temperature both climb. By the time air exits the final compressor stage, it can be compressed to over 40 times atmospheric pressure and heated to several hundred degrees Celsius purely from being squeezed before any fuel has even been added. Why compress it this much? Because compressed air holds more potential energy. When you eventually ignite fuel in that air, a compressed oxygen-dense mixture releases dramatically more energy than burning fuel in loose, thin air. This is the same reason a diesel engine relies on compression to trigger combustion. Compression amplifies everything that happens next. The compressor blades themselves are a materials engineering problem. They're spinning at extreme speeds under massive centrifugal load while handling superheated air. Titanium alloys are common in the earlier, cooler stages. Nickel-based superalloys take over in the hotter stages near the back. Now the air enters the combustor, the heart of the engine. Fuel is sprayed in as a fine mist and ignited. This is where the biggest misconception lives. People imagine a violent explosion, like a bomb going off. In reality, it's closer to a continuous, controlled flame, more like a blowtorch than a bomb. Once the engine is running, ignition only happens once. After that, the flame sustains itself continuously as long as fuel and compressed air keep flowing in. Only about a quarter of the compressed air entering the combustor is actually mixed with fuel and burned. That might sound wasteful, but it's intentional. The remaining 3/4 of the air is used to cool the flame down and shield the combustor walls and turbine from direct exposure to it. Combustion temperatures can exceed 2000 degrees Celsius, hot enough to melt almost any metal on Earth. Engineers manage this not by finding a metal that can survive it, but by using layers of cooling air as a thermal buffer, plus special thermal barrier coatings, so the actual metal surface never experiences the full heat of the flame. This is one of the most underrated engineering feats in the entire machine, keeping a solid metal structure intact a few millimeters away from gas hot enough to vaporize it. The scorching high-pressure gas leaving the combustor now rushes through the turbine. Another set of blades, similar in appearance to the compressor but running in reverse. Here's the elegant part of the design. This turbine is connected by a shaft directly to the compressor at the front of the engine. The expanding exhaust gas spins the turbine spins the shaft, and the shaft spins the compressor blades. In other words, the engine uses part of its own exhaust energy to power its own intake stage. Once running, the engine sustains its own compression cycle. Fuel is only added to keep the cycle going and to generate surplus thrust. After passing through the turbine, the gas still has enormous energy left, and it's forced out through a narrowing nozzle at the rear. As the same mass of gas is squeezed through a smaller exit area, its velocity increases dramatically, and that high-speed exhaust, blasting backward, is what generates the majority of the forward thrust, per Newton's third law from earlier. Now, remember that bypass air we mentioned in the intake stage? On modern high-bypass turbofan engines, that cooler air, which never touched the combustion chamber, rejoins the hot exhaust at the back or exits separately around it. This bypass air actually produces most of the thrust on a modern airliner engine, not the hot core exhaust. It's also quieter and dramatically more fuel efficient because accelerating a large mass of air slightly is more efficient than accelerating a small mass of air violently. The same energy delivered more efficiently. This single design choice is why modern jet engines burn so much less fuel than the engines from 50 years ago. Let's zoom out. A jet engine isn't difficult because any single stage is impossible. It's difficult because every stage has to work in a continuous, self-sustaining loop under extreme mechanical and thermal stress for tens of thousands of hours without failure. The compressor and turbine blades can be spinning at over 10,000 revolutions per minute. The turbine blades sit closer to a blowtorch than any other rotating metal component in any machine built by humans. The whole system has to survive massive temperature swings between a cold runway and a cruising altitude sky, bird strikes, ice, and constant vibration, and it has to do all of this while being light enough to actually fly. This is why jet engine development is one of the most capital-intensive fields in all of engineering. A single modern turbofan can represent decades of material science, fluid dynamics, and thermodynamics research compressed into one rotating assembly. So the next time someone says a jet engine just sucks air in and blasts it out, you'll know the real story. Air is slowed and captured at the intake, squeezed to extreme pressure in the compressor, heated by continuous controlled combustion, expanded through a turbine that powers its own compressor, and finally accelerated out the back to produce thrust. All while a huge volume of bypass air multiplies that thrust efficiently and quietly. It's not one clever trick. It's dozens of engineering problems solved simultaneously, all held in perfect balance, spinning thousands of times a minute, 35,000 feet above the ground. If this kind of breakdown helps engineering finally make sense, That's exactly what Core Mechanics is here for. Subscribe, like, comment, and share with your friends and colleagues for more deep dives into the machines that quietly run our world.